It's been a while, hasn't it? It's been like 4 weeks since part 3 has come out. And yeah, I think I lied when I said like part 4. Sorry, it was going to be the week after part 3. It totally wasn't. But here it is. And it's after Christmas as well. So I hope you had a good Christmas. And a good New Year's after I post this. So, yeah. Anyways, in this part, we are going to find K2 and K3, and we're going to combine the three together, because we found K1 last time, and it was a bit crazy. But K2 and K3 should be better. So, let's just go straight in. Yeah. I forgot to mention, like, the stuff on screen, it's just the things that we derived, and I1 is our target. If you haven't watched the previous parts, I don't know why you would do that, but anyways, K2. So this is K2. There's not really anything special to this. This is really standard, but we're just gonna do it anyways because we kind of have to. So because of the X in the top, I want to do a U sub, and because there's kind of like an X squared at the bottom, that kind of helps as well. So if I write the bottom as X squared cubed plus 1 dx, and then I use a U sub, U equals X squared, and then 2x dx, I'll get a half times 1 over U cubed plus 1 du. And this is a pretty standard integral, I guess, but again, we kind of have to do it. So we're going to use partial fractions. We're going to decompose this into its two things. So it factors into u plus 1, and because it's linear, we've got a constant at the top, and then we'll have a quadratic, which is u squared minus u plus 1, leaving us with a linear thing up top. And we'll multiply both sides by, the u cubed plus 1 on the left. And that will give us a times the quadratic bit plus bu plus c times u plus 1. And then we compare coefficients. So if we have... if we compare the coefficients of u squared, on the left it's 0. On the right it should be a plus b, if I'm not mistaken, because there's au squared and then bu times u. So, yeah, that's that. And then if I'm looking at u, again, on the left it's 0. On the right it's negative a plus b plus c. Yeah, because we've got that, and then bu times 1, and then cu. And then constant term, we've got 1 on the left. And then a plus c. Yes, I think that's fine. Okay, so we have 3 equations with 3 unknowns. We're going to solve this. So equation 1, equation 2, equation 3. I'm going to do 1 minus 2 to get rid of the b. So what will that get me? Well, I'm going to get 0 on the left, and then a minus negative a, which is 2a, and then subtract c. And I'm going to add number 3 to this new equation just to get rid of the c. So we'll have 1 equals 3a, so a is a third. Wow, amazing. And then looking at the first equation, it has to be 0, so a plus b has to be 0, so b is negative a third. And then looking at the third equation, a plus c is 1, so c is 2/3. And there we go, we've successfully found the constant. So we're just gonna put them back in here, and a, b, and c all have a common factor of a third. So basically, we can just write this as, well, I'll write 1 over u cubed plus 1 equals, what was it? A over u plus 1, so that's a third u plus 1, plus, I'm going to pull out a third as well. So we're going to have a third times, what is it, negative 1? Yeah, for b it's negative 1, so it's just negative u plus 2/3, which is 2. So negative u plus 2 divided by the quadratic bit. So, no, that should be a minus u. And that's it. So we've decomposed it, and then I'm just going to put it into the integral. Yeah, so I've just put it into the integral, and then I'm going to pull the third out. Well, I've already done that. I'm going to pull the third out from both fractions, but I'm going to put that outside the integral as well. So that's going to be a sixth of whatever's going on in there, which is a bit dumb, but oh well, right? And then I'm actually going to pull out a minus as well, just so that this can be u minus 2, and then whatever this wants to be. So we're going to do the standard thing, which is to split this up into two integrals, put a big bracket there, and then 1 over u plus 1 du, and then subtract this integral. So the left integral, hopefully you can see what's going on. If you can't, u sub it, and then this will get you natural log u plus 1 in absolute values. But it's 0 to 1, so if you put in 0, it's natural log of 1, which is 0. If you put in 1, it's natural log of 2. So this reduces to natural log of 2. And if you can't tell, I'm trying to be quick right now, because the last video was long, but, you know, don't know how this one will go. Anyways, for the second integral, I'm just going to copy this down, but, you know, for the second integral, I want to do a u sub as well, but I want to u sub the denominator. The thing is, if I do well, not a u sub, maybe we'll do a lambda sub. If I do lambda equals u squared minus u plus 1, d lambda will be 2u minus 1 du, right? And then the thing is, I don't have that at the top. How do I achieve that at the top? Well, I'm going to multiply by 2 and then divide by 2. So the divide by 2, I'm going to put that out front, multiply the numerator by 2 to compensate for that. And then, now I kind of have something similar to this. I'm missing a 3 though, but that's fine. I'm actually just going to write this out on the side just so it's easier for us to keep track of. If I can split this up into two integrals, so that will be 2u minus 1 divided by this, and then I'll have to add 3, I believe. If I add, no, I need to subtract 3. Subtract 3 over this. There we go. And then now I can do my lovely u sub, or my lovely lambda sub, whatever I called it. It'll just be this, and then lambda will be at the bottom, and then d lambda's on top. So that's just natural log of lambda, which is natural log of u squared minus u plus 1 or whatever. Yep, we'll just deal with that. We'll just stick that there for now, and then I'm actually going to pull this 3 out as well. I hope you can follow. I don't know why I'm being so different from other videos. It's been a month. Okay, I don't know what's going on. But, yeah. how are we going to deal with this? We are going to complete the square. So if I were to complete the square, I will divide the middle coefficient by 2. So that will be u minus a half squared. And what am I missing to get to 1? So a half squared is a quarter. So I need to add 3 quarters to get to 1. And then du. And then there's this, like, I think I've mentioned it before, if you have, like, the integral of 1 over u squared plus a squared or something, it's 1 over a inverse tangent u over a. Yeah. So we'll do the same thing. So that's, we have the natural log here, and subtract 3 times 1 over a would be 1 over the square root of this, which is, oh god, which is 3 over root 2, but square root it would be, not 3 over root 2, root 3 over 2. If I square root this entire thing, hold up, my brain's not working. If I square root this, it's root 3 over 2, so I'll get 2 over root 3. Yeah, that's right. And then inverse tangent, u over a, but I have this bit, so that'll stay there. If you're wondering if I can just copy that, you can do another lambda sub, but du equals d lambda in that case, so it doesn't change much. You just put that straight in, and then it's another 2 over root 3, so 2 over root 3, that's multiplied the entire thing, so that turns into 2u minus 1. And so that is the integral. I hope it wasn't too sporadic, that, whatever, I don't know. Anyways, the bounds are from 0 to 1. If you evaluate the 1 bound, let's see. What happens if I do the 1? So if I do 1, let's check out the natural log first. If I do 1, it will give me natural log of 1, which is 0. If I do 0, it will also give me natural log of 1. So that just goes away. And I'll have a negative 3 times 2 root 3. So actually that's just a constant that can be pulled out front. I'll have, if I set u equals 1, I'll have inverse tangent of 2 minus 1, which is 1 over root 3. So inverse tangent of 1 over root 3, that is pi over 6. There we go. So that's pi over 6. And then I'll subtract when I put u equals 0, so that's negative 1 over root 3. So that's negative pi over 6. And so that turns into a plus pi over 6, which turns into a pi over 3, which cancels with that quite nicely, I would say. And then, is it just 2 pi? 2 pi over root 3, yep. So this thing is negative 2 pi over root 3. So this is negative 2 pi over root 3. And so this integral is 1/6 log 2 of 1/2 times that. The two negatives become a positive, and then that's just pi over root 3, because the 2's cancel out. And there we go, that is K2. I hope I did that quickly. If I didn't, oh well, it's going to be a long video anyways, but there you go. That is K2. Right, so this is K3. I'm not going to rush it as much, because K2 is honestly quite easy, and I was taking the mick out of K2. That's why I was kind of rushing it. Yeah, we're going to take our time with K3, because it's a bit weird. I'm going to end up having 4 integrals, believe it or not. So many integrals. out of just one integral. But anyways, this is k3. Again, we're going to try to, like, expand the denominator, but then it doesn't really expand well. But we're going to brute force it. So we have the denominator, which is x to the fourth minus x squared plus 1. And we're going to try to partial fraction decomposition this. And what we are going to notice is that because I've got an x to the fourth and a plus 1 here, I'm going to try to make this a perfect square, because if I do get this a perfect square, I can have a difference of 2 squares because of that x squared in the middle. The way I'm going to make x to the fourth plus 1 a perfect square is that if I have x to the fourth plus 2x squared plus 1, that is a perfect square, but then I don't have minus x squared anymore. So to get that, I'll need to subtract 3x squared. And then I don't have a perfect square in here, but, like, we're going to have to brute force that. So I have a perfect square on the left, which is x squared plus 1 all squared. Yep, and then minus 3x squared. And by the difference of 2 squares, we're going to have x squared plus 1 minus root 3x. But I'm going to put the minus root 3x here, just because it looks nicer. And then plus root 3x for the other bit. So we have this expression now. They're quadratic, so that means our original fraction thingy is going to be ax plus b divided by this fraction plus cx plus d divided by this fraction. And then, again, we'll multiply both sides by x to the fourth minus x squared plus 1. And because these are basically its factors, this has the coefficient of ax plus b, and then the other one has cx plus d attached to it. There we go. And then, again, now we just compare coefficients. So, what coefficients are we going to compare? Let's compare x cubed, because we're lacking that. So if we compare x cubed, let's see. Why did I say we're lacking that? We're not lacking. I was going to say x to the fourth. Sorry, just a side topic. Not a side topic. Right, you know what? I don't even know what I'm saying. It's not 4 in the morning, because it says 4 in the morning in the corner. It's actually 8:30 in the morning right now. The thing is, it's still super early, so I barely know what I'm talking about, but we're going to roll with it. So, anyways, x cubed. We're going to have x cubed. On the left, we don't have a coefficient. On the right, we have a from this bit, and then c from this bit. And then there's no other coefficient for x cubed. So x squared we go. Looking at x squared, we have ax times root 3. So a root 3 plus bx squared, that's 1. And then cx times negative root 3, so that's minus c root 3. And then, what else? Plus d. There we go, plus dx squared. And similarly, we're going to look at x. So we have ax times 1, which is a, and we don't have a coefficient on the left. So x plus 1, and then we have a b root 3, and then cx times 1, and then a d root 3. Negative d root 3, because there's a minus root 3. And let's look at the constants. So we have 1 on the left, and then b and d on the right. So we have that. And we're just going to start solving this. So what I see personally is that we've got an a plus c going on here, but we know a plus c is 0. So this goes away. And the same thing happens with here. So b and d, and then b plus d is 1. So if I get rid of this, that this is actually equal to -1 if I move the b and d to the left. So what I end up with is a root 3 plus, nope, not plus, minus c root 3 is -1. And what else? B root 3 minus D root 3 is 0, which doesn't seem to help that much. What is going on? Right, so because I have a negative C root 3 here, I want a plus C root 3 to eliminate that, and I can get that by multiplying this entire thing by root 3, which doesn't affect it, so I've got a root 3 plus c root 3 is 0. There we go. And then I add the two together. 2 root 3a is -1, and then a is -1 over 2 root 3. And because c is just the negative of a by looking at that, so c is just the positive version of this. And same thing here, actually. This is not entirely unuseful, because what was b root 3 minus d root 3 again? 0. So 0 is that, and so b minus d is actually just 0. Divide by root 3 all over, and then these two simultaneous, add them together, 1 equals 2b. So b is 1/2, and d is 1/2 as well, because 1 equals b plus d. So we have these coefficients. I'm just going to sub them back in. Right, so I've just subbed them in. The first thing I'm going to do is to just switch the positions of these two terms. And you'll see why in a bit. Let me just move them around. But that will make it slightly more convenient. Anyways, we're trying to integrate this thing, remember? So, if we... Was this the integral? Yes, that is the integral. Don't know what's going on. Anyways, yeah, so we're trying to integrate this. So if I just write out I'm just going to write it here, why not? We're integrating this from 0 to 1. And so, if we're integrating this looks like an absolute mess right now, but I do see a few things I can pull out. I can pull out this weird factor here. So let me just do that. So if I pull out 1 over 2 root 3, that reduces to x. I'll have to multiply this by 2 root 3, which means it's just root 3, because 2 root 3 times 1/2 is just root 3. And then that becomes a negative x. That also becomes a root 3. And another thing is that, similar to K2, I'm going to try to do a U sub with this at the bottom, and this requires me to multiply the top by 2 again, because of that x squared. So, if I multiply the top by 2, I'm going to have to divide by 2 as well at the front, so that becomes a 4, and there's a factor of 2 everywhere at the top. And now, I'm prepared to split this into the 4 integrals that I was talking about. So, I have 1 over 4 root 3. And why 4 integrals? Because the derivative of this is 2x plus root 3. And I want that up at the top, but I've got an extra root 3 here, so that's going to be kicked out into a different integral. So that's going to be the integral from 0 to 1 of 2x plus root 3 divided by x squared plus root 3x plus 1. And then I'm going to have the root 3 that's missing. So because that's a 2 root 3, I have to make up for that. And that's going to be in this integral here. And similarly for this one. So, actually, before I do that, I'm going to pull out the minus sign. So there's going to be a negative there. That's going to be positive, and that's going to be negative. So I'm going to have 2x. I'm going to have minus root 3 because I want this minus here. So x squared minus root 3x plus 1. And to make up for that, sorry, this should be a minus. And to make up for that, because, wow, my brain isn't working. So what's happening now? So I've got a 2x minus root 3. So I need to add root 3 to make up for that. X squared minus root 3x plus 1 dx. Do I add root 3? Negative. Yeah, so it's a minus negative root 3. There we go. That should make more sense. Does it? Does it make more sense? So if I put brackets there and then I add that, yeah, so this would become that in brackets. Yeah, and then I expand the bracket, so that becomes a negative. And then these two negatives cancel out to become positive. Just be careful with signs and stuff, but we persevere. So this gives us our nice u-subs, and as I was saying, these two integrals have nice u-subs. The top is literally the derivative of the bottom, so it's going to be natural log of this from 0 to 1. And if I put in 0, that's going to be natural log of 1. So that's 0. If I put in 1, that's going to give 2 plus root 3. How interesting. So I'm going to have 2 plus root 3 here. And I'm going to put this forward first because we have an actual value for that. And similarly, if I do x squared minus root 3x plus 1, 0 is going to give us nothing. Putting in 1 is going to get us 2 minus root 3, and that's still positive. So just normal brackets, 2 minus root 3. And then our two little integrals. So what are we going to do with our integrals? Right. Let's see. We're going to move the root 3 out, just because it's just another annoying factor that we have to deal with. And same thing here. So root 3. And then 1 over x squared minus root 3x plus 1 dx. And we're going to worry about that in a sec. What I want to do is to combine these two, because log properties, this is equal to natural log of 2 plus root 3 divided by 2 minus root 3. And multiplying this top and bottom by the conjugate is going to get us natural log of, so the bottom will be 4 minus 3, because 2 squared is 4, root 3 squared is 3, so 4 minus 3, which is 1, so denominator is 1. And then the top is 2 plus root 3 squared. And that ends up being 4 plus 4 root 3 plus 3. So 7 plus 4 root 3. Let's hope I did that right. Yeah. So natural log of 7 plus 4 root 3. And I think we can do these integrals as well. So, similar to K2, I'm going to complete the square. So this will be 1 over x plus root 3 divided by 2, middle divided by 2, and then squared. So how much do I need to get to 1? So I've got root 3 divided by 2 squared, which is 3 over 4. So I've got a quarter left. And the same thing here, so x minus 3 over 2 squared plus a quarter. And integrating that, I'll just write it out. So we've got this factor out front, natural log 7 plus 4 root 3. And then we've got plus root 3. Right, so let's see. This is our a squared, so our 1 over a is 1 over half, which is 2. So I've got 2 times the inverse tangent of x times 2, because x divided by a, but 1 over a is 2, so it's 2x. 2 times this bit, because again, if you do a u sub, dx equals du, so it doesn't change it. So it's just 2x plus root 3. There we go. And then subtract. Not subtract. What am I talking about? Not subtract. Just plus root 3 times, again, it's 2 because the quarter stays the same, but the sign inside the inverse tangent is flipped. Yes, and then we evaluate this from 0 to 1. There we go. Right, so, that looks like a gamma right there. Let's not do the Euler macaroni constant. But anyways, there we go. Whoa, a lot of things happening. So, right, let's see what I can do. So, natural log 7 plus 4 root 3, and then I'll pull a 2 root 3 out. Right, so let's put in 1 first. So what will happen if I put in 1 first? If I put in 1, that's going to give me inverse tangent of 2 plus root 3 plus inverse tangent of 2 minus root 3. Wow, amazing. So that's in brackets. And then subtract when I put in 0. So when I put in 0, it's going to be the inverse tangent of... Hold on. Inverse tangent of root 3, which is pi over 3, plus the inverse tangent of negative root 3, which is negative pi over 3. So that goes away because they cancel out. And we're left with this thing. Right, so what we're going to notice is that 2 plus root 3 is actually the reciprocal of 2 minus root 3. And you can verify that by multiplying the top and bottom by the conjugate. And then that gives you back 2 plus root 3 because the bottom multiplies to 1 because 4 minus 3, which is 1. So, because they are reciprocals, this is actually 1 over 2 plus root 3. And we know that if you reciprocate an arctan, it's the inverse cotangent. So, we have inverse cotangent of 2 plus root 3. And another identity that I'm going to use, I don't know if it's popular or something, but I know it. So, if the argument is positive, then inverse tangent plus inverse cotangent is always pi over 2. And you should be able to prove that. I'm just not going to help you now. So, all in all, we can get 1 over 4 root 3 times natural log 7 plus 4 root 3 plus 2 root 3 times pi over 2, which is pi root 3. And so, if we decide to rationalize this bit, that's root 3 over 12, I believe. So a quarter times 1 over root 3, but 1 over root 3 is root 3 over 3. So yeah, and then natural log 7 plus 4 root 3, and multiplying this by pi root 3 gives the pi root 3's cancel out, pi over 4. There we go. That's K3. That's K3. Oh my god, we have all of them. We have all of them. So let's plug them in. Right, I'm so excited. Okay, we finally get to finish this. So, before we pack everything up, I'm just gonna recap what we did in the last 4 parts. So what we did is, first we parameterized it into this integral function with the parameter inside the arctan function. Yep, and then we established that this, our target crazy integral thing, is equal to I have 1. And we made use of the fundamental theorem of calculus, because we noticed that if we took the integral of I prime of a, which we explicitly found as well, this would be equal to I of 1 minus I of 0 if we set the bounds to 1 and 0. And I of 0 is just 0, because a equals 0 makes the entire integral 0. So we also explicitly found I prime of a. I'm not going to write that down, but this integral, we found that it was equal to k1 minus pi over 2 k2 plus, well, let me write that properly, plus 2 pi over 3 root 3 k3. And there we go. Let's put in the values. So k1 is 1 over 144 times 4 root 3 pi squared minus 80 times Catalan's constant minus pi over 2 times k2, which was 1/6 of natural log of 2 plus pi over root 3, and plus 2 pi over 3 root 3 times k3, which was root 3 over 12 natural log 7 plus 4 root 3 plus pi over 4. And let's expand everything out. So, we'll start from the beginning. So, 4 root 3 divided by 144. What's wrong with my voice? Sorry. What is wrong with my voice? Okay. Anyways, 4 divided by 144, that should be 36. So, it's pi squared divided by 36 times root 3. Minus 80 divided by 144, which is 5/9. Catalan's constant, minus pi 12ths natural log of 2, and minus pi squared over 2 root 3. No, pi squared over 12 root 3, actually. Of nothing. Pi squared over 12 root 3, and we rationalize it, kind of, by multiplying root 3 on the top and bottom, giving us pi squared over 36 times root 3. And the last bit, where the root 3's cancel out, giving us 2 divided by 36, which is pi over 18, times this natural log thing, and plus pi over 4 times that, which gives us pi over 6 root 3. Yep, and then multiplying root 3 on top and bottom gives us pi over 18 times root 3. Oh, pi squared, sorry, because 2 pi's. And then we do some simplification. So we've got this bit that's identical to this bit, so they just cancel out. And rewriting it in a better order, we've got pi squared over 18 times root 3 minus pi over 12 times the natural log of 2 plus pi over 18 natural log 7 plus 4 root 3 minus 5/9. Catalan's constant. And last thing we're going to do is to combine these two terms together because they both have a natural log. So I'm going to make this easier for myself, and because if the natural logs are the same sign, I can multiply them. So I'm going to turn this into a minus at the cost of taking the reciprocal of this, because it's to the power of -1 now, because, yeah, so I multiplied by -1, and then, so I have to exponentiate it by -1. And the reciprocal of this, if I multiply by the conjugate, this is going to give us 1, because this is equal to 49 minus 4 root 3 squared, which is 48. So this is exactly the conjugate, which is 7 minus 4 root 3. And so let's take out the minus sign from both terms. And now we try to combine them by making a common denominator. So to make a common denominator, we're going to choose 36 as the lowest common multiple. That means we have to multiply by 3 for the first term thing in the brackets. And multiplying the bottom by 3, we're going to get 36. Multiplying the top by 3, we're going to exponentiate the 2 by 3, because properties of logs. And the same thing we're going to do to the second term. We're going to multiply by 2 this time and square the inner bit. And squaring the inner bit, it's going to give us 49 minus 7 times 4 times 2 is 56. And 4 root 3 squared is 48. So we are going to have, what are we going to have? 97 minus 56 root 3. So 97 minus 56 root 3. And that is an 8. So in the end, we're going to get pi squared divided by 18 times root 3 minus pi over 36 natural log 8 times 97 minus 56 root 3. 8 times 97 is 776. 8 times 56 is 448. Root 3 minus 5/9. Catalan's constant. There we go. That's our answer. That's our answer. And I'm going to write our nice little integral over here. Is it 0 to infinity? Yep, it's 0 to infinity. I forgot what the actual integral was. You know what? It's fine. And that's x cubed plus 1. I don't have space for the dx. Come on, come on. Come on. Move. Move. Okay. Dx is equal to that. And I'm going to put this in a lovely box. There we go. It's not even a good box. Right, I need to draw a good box. There we go. Come on, come on, come on. Draw a box! Why is it messing up at this moment? Please. Oh my days. That's good enough. Right. I'm just gonna rewrite the integral so that it's not touching the box. There we go. There we go. This is it. This is it. This is literally it. Right? Video end. Okay, goodbye. I hope you liked it. Yay.